Sorry about that, guys. So this is the never-ending lecture apparently, but let's go ahead and get screen share going again and see if I can get it right this time. Okay, so remember we were trying to determine if event 1 and 2 were collectively exhaustive. So that was one of the questions we're trying to answer. Are events 1 and 2 mutually exclusive? We determined that they are mutually exclusive. And now we're trying to determine if they are collectively exhaustive. And so the way that we do that is we draw a Venn diagram. So we start again with the possibility space, which consists of either light rain or heavy rain, rain of some form. And then within that possibility space, we have well-compacted clay layer, or we have the event where there are holes in the geotextile. And so we wanted to look at event 1. Again, event 1 is going to be the intersection of this particular form of construction, either poorly compacted clay or holes in the geotextile with a heavy rain event. And we can bring that intersection inside the parenthetical there. And so we basically have a union of these two intersections, W complement E and HE. So let's think about this one a little bit. W complement E, let me give my little red pointer here. So W complement E, basically we're looking for the intersection between everything outside of W and E. And so that's going to be the white space that's indicated here, W complement E minus the little bit of white inside of W. So that we wouldn't have until we union it with HE, because that little extra bit is going to be the intersection of H and E, which is the sort of half sort of hemisphere of H. And so when we add that in through the union, we end up with this entire white space here. So that is our event 1. It's a very oddly shaped space. Event 2 is the intersection of W complement H and E complement. So let's think about that a little bit. So W complement is going to be everything outside of W. We intersect that with H. So that's just going to be the portion of H outside of W, which is that. And then we intersect that again with E complement, which is just the upper hemisphere of that portion of H, which is outside of W. And so that's given by the black. So E2 then is the black region, E1 is the white region. And if we look at those two regions together, so if we union them, they definitely do not equal the whole sample space. And so we can conclude that the union of, that should be E1, union with E2 is not equal to the sample space. And therefore, these two events, E1 and E2, are not collectively exhaustive. All right, we have yet another question. Determine the probability that this containment facility will leak during a rain event. And so that's during any rain event, whether it's heavy rain or a light rain. And basically all that we need to do there is, if you think about it, we have two possible ways a leak can occur, event 1 and event 2. And we're going to condition it on a rain event, which is just our possibility space S. So that's the same as saying the probability of event 1 union with event 2. We know from our previous analysis that event 1 and 2 are mutually exclusive, and so we don't have to worry about the cross product term in our addition rules. So we can just write the probability of E1 plus the probability of E2, which we've computed, and that gives us this final result. So during any rain event, there's a 15% chance roughly that there will be a leak. All right, so let's move on to another problem. And there's, again, just like with the previous problem, there's a whole series of sub-problems. Some of these sub-problems involve the theorem of total probability. Some of them involve Bayes' theorem. So it gives us a little bit of practice with some of the concepts really toward the end of chapter 2. Okay, here's the setup. The maximum intensity of the next earthquake in a city may be classified for simplicity as low, medium, or high, with relative likelihoods of 15 to 4 to 1. So we notice these guys add up to 20, and so that means that the likelihood of a Low intensity earthquake is going to be 15/20, medium 4/20, and high 1/20. Suppose also that buildings may be divided into two types, poorly constructed, P, and well-constructed, W. About 20% of the buildings in the city are known to be poorly constructed for earthquake resistance. It is assumed that a poorly constructed building will be damaged with a probability of 0.1, 0.5, and 0.9 when subjected to a low, medium, or high intensity earthquake, respectively. However, a well-constructed building will survive a low-intensity earthquake, although it may be damaged when subjected to a medium or high-intensity earthquake with a probability 0.05 or 0.02, respectively. Okay, that's a real mouthful for a problem. What is the probability that a well-constructed building will be damaged during the next earthquake? Okay. What do we know? So let's just kind of go through all of the information that they gave us in that paragraph in word form and see if we can write it out as mathematical statements. So let's use some symbols first. Let's denote L as a low intensity earthquake, M as a medium intensity earthquake, and H as a high intensity earthquake. And then we can write down EQ, excuse me, as the occurrence of an earthquake. And so the probability of a low intensity earthquake conditioned on an earthquake occurring is going to be 75%, medium conditioned on EQ, 20%, and high conditioned on EQ, 5%. Notice that these guys add up to 100%, which is good because basically, really they're mutually exclusive, right? And they're also collectively exhaustive because an earthquake of any form is divided into low, medium, and high. Furthermore, we're told that buildings can be either poorly constructed or well constructed, and that about 20% of the buildings in the city are poorly constructed. So the probability of a poorly constructed building is about 20%. These are mutually exclusive, so that means that the probability of a well-constructed building is going to be the complement of a poorly constructed building, and so that's going to be 80% for a well-constructed building. We also know that the probability of damage, so we're going to denote D as damage to a building, if it's poorly constructed and also we have a low intensity earthquake, so that's the intersection of these two events, CP and L, is 10%. So that was one of the problem statements. Likewise, the probability of damage if you have a poorly constructed building during a medium earthquake is 50%, and the probability of damage if you have a poorly constructed building during a high intensity earthquake is 90%. Okay. On the other hand, the probability of damage if you have a well-constructed earthquake during a low intensity event is 0. The probability of damage of a well-constructed building during a medium intensity earthquake is 5%, and the probability of damage given a well-constructed building during a high intensity earthquake is 20%. So that's pretty much all of the information that they gave us. And so we come back to the first question, which is, what is the probability that a well-constructed building will be damaged during the next earthquake? To get this, we really need to invoke the theorem of total probability, because what we're asking for is not something that they've given us. We want to know the probability of damage given that we have a well-constructed building. Or another way to ask that question or state that question would be, given that you have a well-constructed building, what is the probability of damage? And that's going to depend on whether there's a low, medium, or high intensity earthquake, right? So we're not given any of that information. We just want to know if there's an earthquake, what is the probability there'll be damage if the building is well constructed? And so we have to use the theorem of probability, which allows us to write this as the probability that the building will be damaged given a low or condition on a low intensity earthquake times the probability of a low intensity earthquake plus the same thing for medium and high intensity earthquakes. And we, it turns out, have most of the things that we need. So let's kind of look this over. So we know what the probability of a low intensity earthquake is. It's if there's an earthquake, it's going to be 75% chance that it's a low intensity. It's a 20% chance that it's a high intensity, and it's a 5% chance that it's 20% chance that it's a medium intensity, and 5% chance that it's high intensity. Likewise, we're given all of these conditional probabilities. Two, we know that the probability of a building being damaged if it's well constructed during a low intensity earthquake is 0. We know that the probability of damage of a well constructed earthquake during a medium intensity earthquake is 5%. And we know the probability of damage of a well constructed building during a high intensity earthquake is 20%. So we multiply out all these numbers, and the answer is 2%. So the probability that a well-constructed building will be damaged during the next earthquake is 2%. Next question is, what proportion of the buildings in this city will be damaged during the next earthquake? And here we basically use the theorem of total probability again, but we apply it to total damage. So we've got two kinds of buildings that can be damaged. We've got poorly constructed buildings that can be damaged, and we have well-constructed buildings that can be damaged. So we can write this probability of damage as the probability of damage given that we are talking about a poorly constructed building times the probability of a poorly constructed building plus the probability of damage if the building is well constructed times the probability of it being well constructed. We know what these two probabilities are. The probability of the building being poorly constructed in the city is 20%. We got that from the problem statement. And because these are mutually exclusive, the probability of the building being well constructed is going to be 80%. We also know what the probability of damage given a well-constructed, if we have a well-constructed building, what the probability of damage is during an earthquake. That was the what we solved for in the last problem, and that worked out to be 2%. So we've got that one taken care of too. So the only term that we only expression or probability that we don't know at this point is this one here. It's the probability of a poorly constructed building being damaged. So we have to calculate that out. And again, we invoke the theorem of total probability because the probability that a poorly constructed building will be damaged during an earthquake is going to be, again, the probability that it's damaged during a low intensity earthquake times the probability of the low intensity earthquake, and so forth and so on for the medium and the high intensity earthquakes. And then we just plug and chug because we know all these numbers. We were given that the probability of damage of a poorly constructed earthquake during a low intensity earthquake is 10%. And then we know the probability of that during the next quake is 75%, the low intensity earthquake, and so forth. And when we calculate all that out, we get 22.22 or 22%. So that is our number here. And so we can then plug all of these numbers in, 0.22 times 0.2 plus 0.02 or 2% times 0.8, and we get 6%. So 6% of the buildings in this city will be damaged during the next earthquake, given what we know about those buildings. And then another question is, if a building in the city is damaged after an earthquake, what is the probability that it was poorly constructed? You can imagine that if you were an insurance company, this might be a very interesting question to try to get an answer to. First, we can just write out what the probability statement would be. We're really asking, given that the building was damaged in the earthquake, what is the probability that it was poorly constructed? And we haven't been given this conditional probability in the problem statement, but we're given something very similar, or not really similar, but kind of symmetrically similar. That is, we were given the conditional probability with the terms flipped. So we were given the probability of that if we had a poorly constructed building, we were given the probability that it would be damaged. That was 22%. Actually, it wasn't given. It was something that we calculated from the last problem. So we have this. We'd like to calculate that. How do we flip the order of those two terms? Well, remember, we use Bayes' theorem. So Bayes' theorem allows us to do that. It allows us to calculate the conditional probability here from the conditional probability with those two terms flipped. And so we know this term in the Bayes' theorem. We also know the probability of poorly constructed buildings in the city. And we also know the probability of damage occurring from the problem that we solved a second ago. And so we plug all those numbers in, and we end up with the final result of 73%. So basically what that means is that if you have a building that's damaged in the earthquake, there's a 73% chance that it was poorly constructed. And that's all I have for you today. So thanks for being patient with me and suffering through all of the various versions of this PowerPoint presentation. Okay. See you in class.